Hello and welcome to Algebra 2 Lesson 11. In this video, we're going to learn about linear inequalities in one variable. So by the time you get to an Algebra 2 course, hopefully you've had at least some experience with solving a linear inequality in one variable. But even if you haven't, we're going to cover all the details involved with this process, and it's going to serve us well in the next lesson and the lessons after that because we're going to need this as a basis. Now we start off with a generic example where we have ax plus b is less than c. So this is something you'd probably see in your textbook. And we can say that a, b, and c are real numbers. So basically anything you can think of at this point could be plugged in for a, b, and c with one exception. A, the coefficient of x, is not allowed to be equal to 0. And that's because if I multiply 0 times x, I'd get 0, and I'd be left with b is less than c. Now, there's one other thing we want to note. We have a less than here. This is a less than. I could replace this with a greater than, or a less than or equal to, or a greater than or equal to. All of those would be equally valid in this generic example. We just have to choose one of them. We just happen to choose a less than. So we have ax plus b is less than c, where again, a, b, and c are real numbers. A is not allowed to be 0, and the less than could be a greater than, a less than or equal to, or a greater than or equal to. So here are just a few examples, and we'll get to solving these in a minute. So we have 2x minus 7 is greater than 5. We have negative 3x plus 10 is less than or equal to 17. And then we have 0.25x is greater than or equal to negative 2. So the main difference between an equation and an inequality, with an equation, something like x equals 7, x can be one value there. It can be 7. So on the number line, it's basically represented with just this. This is x is equal to 7. With x is greater than 7, if I was to think about that, that's a range of values. I can plug in anything for x that's larger than 7, and I will get a true statement. I could plug in an 8, a 9, a 10, a 1 million, a 1 billion. As long as it's larger than 7, it's good to go. Now graphically, and we covered this in the last lesson, at 7 I would put an open circle, or I could put a parenthesis facing to the right. I typically stick with a parenthesis. And I would shade everything to the right. What this means is that 7 is not included in the solution. That's why I have a parenthesis there. Because x is strictly greater than 7. If I plugged a 7 in for x, it wouldn't be true. 7 is not greater than 7. So that's not included, but anything larger than 7, anything to the right of 7 is. So that's why I shaded everything to the right, and I shaded this arrow to say, hey, this is going to continue forever and ever and ever. So anything you can pick that's larger than 7 would work as a solution. All right, so now let's talk a little bit about how we'd solve a linear inequality in one variable. And essentially, we use the same techniques as we use when we're solving a linear equation in one variable. So you'll recall when we're solving equations, we had this property known as the addition property of equality. That told us we could add the same value to both sides of an equation, and we'd maintain the same solution. Well, we have a similar property when we work with inequalities. So it's called the addition property of inequality, and it's the same thing. It allows us to add the same value to both sides of an inequality now, and we don't change the solution. So if I see something like x minus 2 is greater than 7, this is a one-step inequality. So basically all I need to do to isolate x is just add 2 to both sides of the inequality. This would cancel, and you would have x is greater than 9. As another example of this, if I have x plus 8 is less than or equal to 5, again, think about isolating x. I just need to subtract 8 away from each side of the inequality. And so this would cancel, and I would have x is less than or equal to 5 minus 8 is negative 3. All right, for the next property we're going to talk about, it's a little different than its counterpart that is used when we're solving equations. You recall that you have a multiplication property of equality. And with this property, we can multiply both sides of an equation by the same non-zero value, and we will not affect the solution. Well, here, with the multiplication property of inequality, it's different because if I multiply both sides of an inequality by the same positive value, it's the same thing. I'll have the same solution. I don't have to do anything. I don't have to worry about anything. We're basically good to go. You can't use 0 because of the properties of 0. If you multiply by 0, you get 0, so you can't use 0. Anything that's negative, any value that's less than 0, if I multiply both sides by a negative, I've got to flip the direction of the inequality. So a less than becomes a greater than. A greater than becomes a less than. So basically your inequality symbol will flip. As an example of why this occurs, if I have 2 is less than 5, that's true. 2 is a smaller value than 5. If I multiply both sides by a positive, okay, for example, let's say 3. So 2 times 3 would be 6, and 5 times 3 would be 15. 6 is still less than 15. This is true. But if I took this original 2 is less than 5, and I multiplied both sides by a negative, let's just keep it simple and say -1. What's going to happen is I'll have -2 is less than -5. This is now false. Why is it false? Because I started out with a bigger number here. When I applied a negative to it, it became a bigger negative, right? -5 is a bigger negative than -2. A bigger negative is actually a smaller value. You think about the way a number line works, a bigger negative is to the left, right? And as we go to the left, numbers actually get smaller. And it's a hard concept to kind of wrap your head around because generally speaking, until we get into algebra, we think of the number 5, forget about the negative part, as being larger than 2. So that kind of sticks with us for a while until we can shake free of it, okay? So -5 is a smaller value than -2. So for this, we need to flip it. So we're going to flip. And so if I change the direction of the inequality, meaning I go from a less than to a greater than, this becomes true. Okay, this now becomes true. -2 is greater than, or is a larger value than -5. All right, so let's look at an example here. We have 2x is greater than 10. So we know if we had 2x is equal to 10, we divide both sides of the equation by 2, we get x equals 5. It's the same thing here. I want to isolate x, and so I want to divide both sides of the inequality by 2 so that I can do that. So this cancels with this. I get x is greater than 5. Because I divided both sides by a positive, I didn't have to flip the direction of the inequality symbol, right? It stayed as a greater than. If I would have had a situation where it was, let's say, -2x is greater than 10, well, in this scenario, I divide both sides by a -2, I've got to flip the direction of the inequality. Right now, it's a greater than. It's got to become a less than. So it's the symbol flips. So this becomes a less than, and this will become x is less than -5. All right, let's say we saw something like -1/2 x is greater than 3. What would I do to isolate x? So -1/2 x is greater than 3. Well, I want to get x by itself, and what I can do is I can multiply both sides of the inequality by the reciprocal of this, so that's -2/1, or basically -2. And so this is going to cancel with this. But what I've got to remember, again, because I multiplied by a negative, and I'm working with an inequality, I've got to flip the direction of the inequality. It's a greater than, so it's got to become a less than. So the symbol there, again, it's a greater than, it's going to become a less than. So this is x is less than, 3 times -2 is -6. All right, so now that we have those two properties under our belt, it's time to look at some sample problems. So we have that 7 is greater than or equal to, we have 6x minus 5 minus 4x. So just like with an equation, I'm going to simplify each side first. So I have 7 is greater than or equal to. We have 6x minus 4x, that's 2x, and then minus 5. Let me make this a little cleaner. So now I want the variable term on one side of the inequality, the number on the other. So I can simply add 5 to each side of the inequality. 7 plus 5 is 12. So 12 is greater than or equal to, we have 2x. To get x by itself, I would divide both sides by 2. Now that's a positive number, so I don't need to do anything to the inequality symbol. This cancels with this and gives me 6. So that's greater than or equal to, and then we have x. Now, typically, I like the variable to be on the left. And I think it makes it easier when we start graphing and using interval notation. So to flip it, if your symbol is pointing to x, that means x is less than or equal to 6. These are the same. 6 is greater than or equal to x, or x is less than or equal to 6. It's just easier to read this because typically we read from left to right. There's two things I want to show you real quick. In our last lesson, we showed how to write something in interval notation, and we showed how to graph an interval on the number line. You might have missed that lesson, and that's fine, because I'm going to show you really quickly how to notate this solution. So the first thing with interval notation is you have basically a value here, a comma, and a value here. So this right here we think of as the smallest, and this right here we think of as the largest. So when we think about x is less than or equal to 6, what is the smallest value that x can take on? Well, there's not going to be one because x is less than or equal to, so any value less than 6 that you can think of is going to work. And that goes on forever and ever and ever. I could do -1 trillion. That would work. So to show this, we use infinity. And specifically there, because it's in the negative direction, we use negative infinity. Now, when I use negative infinity or positive infinity, what I place next to this is a parenthesis. The parenthesis says it's not included, okay? So the smallest value doesn't exist, so we use negative infinity. Now, for the largest possible value, we know it's 6. X can go up to and include 6. So I put a 6 there, and then because 6 is included, I use a bracket, okay? This means is included. So 6 is the largest value and it's included, so we use a bracket. Now graphically, it basically looks like this. Let's go up to a graph. Let me write my solution here. It's x is less than or equal to 6. So on a number line, I would find 6, which is right here. And I can put either a filled in circle like this, or I can use a bracket that faces towards the solution region. The solution region is going to the left because we have a less than. Let me make that a little better. And I want to shade everything to the left. So all these values that satisfy that inequality. And I can't list all of them, so I'm going to shade that arrow to say the solution continues forever and ever and ever. Now looking at the graph and looking at interval notation, you can see some similarities. We use a bracket at 6. We use the bracket at 6. And again, that tells us that 6 is part of the solution. And then it continues forever and ever and ever. We have this arrow here that's highlighted. You can kind of think about this being that. That arrow tells us it continues forever and ever and ever. In interval notation, we express this by saying negative infinity is in place of the smallest value because we don't really have a smallest value. So before we kind of move on, you know in Algebra 1 I checked almost everything. In Algebra 2 I'm not checking as much stuff just so we can get more in. But I want you to know how you can go about checking your answer for this. It's a lot more tedious than checking an equation. The first thing is you would replace your inequality symbol with equals. So let me erase this real quick. I have some room to work. And so if I did that, I would put 7 is equal to 6x minus 5 minus 4x. Then just take your solution and do the same thing. Replace the inequality symbol with equals. So if I put a 6 in for x, do I get a true statement? So this would be 2x minus 5 equals 7. If I plugged in a 6 there, 2 times 6 is 12. 12 minus 5 is 7. So yes, that works out. So 6 is your boundary point. It separates the solution region from the non-solution region. And you can even see that graphically. At 6, we have a separation where 6 works and anything to the left of 6 works, but anything to the right of 6 doesn't. So this is a non-solution region. And this right here is a solution region. So 6 is your boundary. And you'll hear me talk about that a lot moving forward. Now, once you've established that, you just check a number on each side. So we'll do that with the inequality there. And I'm just going to simplify the inequality and make it a little easier for us. So 7 is greater than or equal to, we know this would be 2x minus 5. If I check 8, it shouldn't work because x has to be less than or equal to 6. So if I plugged in an 8 there, I'd get 16 minus 5, which is 11. So 7 is greater than or equal to 11. That's false. That's what we expect. 8 should not work, right? Because we're saying x has to take on a value that's less than or equal to 6. So that's good. Now the next thing we want to do is we want to check a value that is less than the number 6. So let's check 5. So 7 is greater than or equal to, again, this simplifies to 2x minus 5. If I plug in a 5 for x, I get 2 times 5, which is 10. 10 minus 5 is 5. So I get 7 is greater than or equal to 5, and that is true. 7 is certainly greater than 5. So you can see that it's more tedious to check these. You've got to establish the boundary, and then you've got to check one on each side of the boundary. So one in the non-solution region, we checked 8, and it didn't work, so that's right. Then one in the solution region, we checked 5, that worked, so that was right. All right, so let's kind of roll through these now. So I have 1 plus 6 times the quantity 6 plus 4v, and this is greater than negative 27 plus 8v. All right, so let's simplify each side now. So we have 1 plus 6 times 6 is 36, plus 6 times 4v is 24v, and this is greater than negative 27 plus 8v. So 1 plus 36 is 37, plus 24v is greater than negative 27 plus 8v. So let's subtract 8v from each side of the inequality. And let's subtract 37 away from each side of the inequality. So this is going to cancel, and this is going to cancel. 24v minus 8v is 16v. And this is greater than negative 27 minus 37 is negative 64. So to get v by itself, I divide both sides by 16. And I'm dividing by a positive there, so I don't have to do anything special. So this cancels with this, and I get v is greater than, we have negative 64 over 16, which is negative 4. So let me erase everything real quick. So again, we found that v was greater than negative 4. So typically your book or your teacher is going to ask you to do two things once you get a solution. Again, write it in interval notation and graph it. So in interval notation, again, we have these two blanks where we have the smallest and we have the largest. And technically, I'm going to put what? Negative 4 here as the smallest. Is negative 4 actually the smallest value that v can take on? No, it's not. It's as close as we can get to thinking about it, though. I can't possibly list the smallest value. To show that, I'm going to put a parenthesis next to negative 4 to say it's not included. But anything larger than negative 4 would work. If I had negative 3.999999978, that would work. Because looking at a number line, that would be larger than negative 4. But again, anything that's negative 4 or smaller will not satisfy the inequality. What about the largest value that this can take on? Well, again, because this is going to go forever and ever and ever in the right direction, we use infinity. And with infinity, we always use a parenthesis. So again, it's not the smallest number technically, but we use this concept to notate things, okay? So anything larger than negative 4 up to infinity. Now, graphically, we would show this in a similar way. Negative 4 is not included, so I'd put a parenthesis that faces to the right, and then I would shade everything to the right, everything in the solution region, including that arrow to say, hey, this continues forever and ever and ever. Some people will even put an infinity out here to show that. And additionally, you might see this in your textbook. You might see an open circle like this. It's open to show that negative 4 is not part of the solution set. All right, for the next one, we're looking at 6 times the quantity 3x plus 9 is greater than 12 times the quantity 4x minus 8. So 6 times 3x is 18x, plus 6 times 9 is 54. This is greater than 12 times 4x is 48x, and then minus 12 times 8 is 96. So I want to subtract 48x away from each side of the inequality. And I know that this is going to cancel. I also want to subtract 54 away from each side of the inequality. This is going to cancel. 18x minus 48x would be negative 30x. And this is greater than negative 96 minus 54 is negative 150. So now to get x by itself, I'm going to divide both sides by negative 30. But remember, I'm dividing both sides by a negative, so this has to be flipped. Right now, it is a greater than. I flip the direction, it's going to become a less than. So x is going to be less than negative 150 over negative 30 is going to be 5. Let's erase everything. So again, we have that x is less than 5. In interval notation, again, we think about this concept of a smallest value and a largest value. And again, that's not technically correct, but that's how we think about it. So x is less than 5. The largest value that this can take on is not 5, but anything smaller than that. So 4.99999999978, for example. So I put a parenthesis next to 5 just to say that it's not included. What's the smallest value this can take on? Well, it's going to continue forever and ever and ever in the left direction because it's anything less than 5. So negative 1 trillion, for example, would be a solution. So I use negative infinity. And again, if I use positive or negative infinity, I always put a parenthesis next to it. Now graphically, x is less than 5. Find 5 and put a parenthesis that faces left, or put your open circle, again to show that 5 is not included, either one. And then shade everything to the left. So you shade all this in the solution region, including the arrow. And again, some people like to put a negative infinity out here to show that it's just going forever and ever and ever in that direction. All right, so we also have ones that have fractions involved. So just like we saw with equations, we can multiply both sides by the LCD. Now, I'm going to simplify before I start. So we have b plus 8/3 minus 2b is less than 5/2 b plus 1 minus 4/3 b plus 17/18. What can I do? Well, I know b minus 2b would be negative b plus 8/3 is less than. Nothing really I can do here without working with fractions. So let's just write 5/2 b plus 1 minus 4/3 b plus 17/18. What would my LCD be here? I'm looking at denominators of 3, 2, 3, and 18. Obviously, it's going to be 18. So we're going to multiply both sides of the inequality by positive 18. So I don't need to flip anything. 18 times negative b is negative 18b plus 18 times 8/3. 18 would cancel with 3 and give me 6. 6 times 8 is 48. This is less than, if I have 18 times 5/2, 18 would cancel with 2 and give me 9. 9 times 5 is 45. Then times b plus 18 times 1 is 18. Then we have 18 times negative 4/3 b. We know that's negative. 18 divided by 3 is 6. 6 times 4 is 24. So minus 24b. Then lastly, plus 18 times 17/18. 18s would cancel. You just have 17. All right. So nice and easy now. On this side, I can do a lot of combining. 45 minus 24 is 21. So 45b minus 24b is 21b. Then 18 plus 17 is 35. And over here, I still have my negative 18b plus 48. So I want all of my variable terms on one side, all the numbers on the other. So let me go ahead and subtract 48 away from each side of the inequality. So that's going to cancel. And let me also subtract 21b away from each side of the inequality. So that's going to cancel. If I do negative 18b minus 21b, that's going to give me negative 39b. And this is less than 35 minus 48 is negative 13. So now we divide both sides of the inequality by negative 39. And again, if I'm dividing by a negative or I'm multiplying by a negative, this has to be flipped. So this becomes greater than from a less than. So this cancels, and I've got b is greater than negative 13 over negative 39. The negatives cancel. 13 over 39, each is divisible by 13, so you get 1/3. So b is greater than 1/3. So again, we have that b is greater than 1/3. So we can start out with interval notation. Again, on the left, we want the smallest value. Now, 1/3 is not technically the smallest value, but we're putting it in there next to a parenthesis to say that it's not included. But anything larger than 1/3, even if it's a small amount larger than 1/3, a microscopic amount larger than 1/3, would work. So 1/3 is not included, then comma. This continues forever and ever and ever in the right direction. So we put infinity here. We put a parenthesis there. We always use a parenthesis with infinity. So graphically, I would find 1/3. Now I don't have a notch for that, so I'm going to create one. Let's just say 1/3 is about right there. Let's say this is 1/3. And I'm going to put a parenthesis there. Or again, you can use that open circle technique, doesn't matter. And then I'm going to shade everything to the right, everything in the solution region, including that arrow. And again, you can put an infinity out here to say 1/3 is not included, but anything larger than 1/3 works as a solution for this inequality. All right, so the last thing we want to cover is a three-part inequality. So we saw these in Algebra 1. And basically what happens is you have this guy in between two inequality symbols. So 8 minus 5a is greater than 8, and it's less than 38. So both the conditions have to be met. So what's going to happen is you're going to do one of two things. You can separate these and solve them, and then put it back together in the end, which is more work. Or you can solve it doing the same thing to each part. So in other words, I want to isolate a in the middle. So what I do is I would subtract 8 away from each side to begin. So then 8 minus 8 is 0, and this is less than. This would be 0, so I'd have negative 5a. And then less than 38 minus 8 is 30. Now if I want a by itself, I would divide each part by negative 5. But remember, if I'm dividing by a negative, I've got to flip the direction of the inequality. Right now, these are less than. So if I flip the direction of that symbol, it's going to become a greater than. So this would be 0 over negative 5 is 0. I'd have a greater than. This would cancel, and I'd have a. And then a greater than. 30 over negative 5 is negative 6. Now, you don't want to keep it like this. You want to put it in the direction of the number line. Negative 6 is to the left of 0, so you want it lined up that way. So we would put negative 6 is less than a, which is less than 0. Or a is greater than negative 6, and also it's less than 0. Looking at a number line, it's a range of values, not including negative 6, so I'd put a parenthesis there. So anything larger, up to but not including 0. So I'd put a parenthesis there. I would shade everything in between. This is just telling me that a is a value that's between negative 6 and 0. In interval notation, again, we use this concept of the smallest and the largest. Negative 6 would go in this spot for the smallest. It's not included, so I put a parenthesis there. 0 would go in the spot for the largest. It's also not included, so I put a parenthesis there. So here's interval notation, and here's graphically. All right, let's look at one final problem. And again, these three-part inequalities are no more difficult. So we have 7v minus 5 is greater than or equal to negative 61, and it's less than or equal to negative 40. So again, do the same thing to each side. So plus 5 here, plus 5 here, plus 5 here. So negative 61 plus 5 is going to give me negative 56. And it's less than or equal to, this cancels, so I'll just have 7v. And it's less than or equal to, negative 40 plus 5 is negative 35. So now what I want to do is divide each part by 7 so I can isolate v. And what's going to happen is negative 56 over 7 is negative 8. This is less than or equal to. We'll have v by itself now because this cancels. And this is less than or equal to. Negative 35 over 7 is negative 5. So v is greater than or equal to negative 8, and it's less than or equal to negative 5. Let me drag this solution up. So graphically, If I located negative 8, it's there. So it's included in the solution set. So I'm going to put a bracket here that faces to the right. Same thing with negative 5. It's included in the solution set. So I'm going to put a bracket there. This one's going to face to the left. And I shade everything in between. So what this is telling me is that v can be any value starting from negative 8 going up to and including negative 5. Now in interval notation, again, smallest, largest. Let's think about that. The smallest value v can take on is negative 8. Now negative 8 is included. It's part of the solution, so I use a bracket. And it goes up to and includes negative 5. So the largest value would be negative 5. Again, I'm using a bracket because it's included. So your solution here is that v is any value that is greater than or equal to negative 8 and less than or equal to negative 5. So again, starting from negative 8, including negative 8, going up to and including negative 5.